So, hello everybody, and welcome to our first official Calc 1 class um, for remote stuff. So, hopefully you guys can all see me. I got a camera, so that should be working out nicely. And hopefully my voice is cutting out a little less. You might hear a little bit more background noise from me. Again, I'm working through some things to try and cut out some background noise. But for now, this is what we got. So, we'll go with there. For what it's worth, if I stream on a third-party service, the background noise problem is already fixed because I already have something that's doing it through OBS. So we'll see. I'll figure something out. Anyways, um, do you have a question or something you wanted to say, Isaiah?
Yeah, I was just gonna ask if you still have that problem with your headphones where every time you say questions, it freaks out.
I'm not checking. I probably do. It hasn't happened to me in the last 2 days, so crossing my fingers that my enunciation maybe has improved in a way, or I just managed to trip some setting somewhere. So we'll go. Um, if that does happen, I will ask you to repeat yourself after I get my sound back. Hi, Monique. I
You
heard
guys hear
something.
me?
Yeah, we can hear you.
Yay! Sorry.
Awesome. Cool. All right. So math wise, oh, I guess one more thing to talk about a little bit. Exam wise, I still haven't landed 100% on what I want to do, but I will say that the exams will probably be take home exams. I mean, they're not really take home exams because I assume you're all currently home, so they're more like keep home exams. But regardless, that means that it's likely going to structure itself a little bit differently. I'll probably still give you a set of questions and ask you to choose from them, but I'm more likely to say, hey, here are six big, hard, difficult problems, and I want you to do like a full write up on three of them or something like that. So we'll go over that a little bit more in depth, but you can think of it as sort of like a hybrid between a take home test and like a paper or an assignment of some sort. So again, we'll talk more about that once we get closer to the exam. So, all right. If there are no other questions, so if anybody has any questions about administrative stuff or what the plan is from here on out, speak now or speak later, or poke me in chat or something like that. I can see the chat at the same time as all of this, so we should be good. Okay. In that case, let's start doing some math. So essentially, our goal for the next week or so is we're going to be getting to deal with a topic in calculus that's called optimization, and basically the idea is that there's a lot of different situations that can be modeled mathematically that sort of have a kind of a push and a pull. Like if you have a quadrilateral, right? And you want to know what's the largest area you can have for a certain perimeter, right? You can increase the length of one side or you can increase the length of the other side, and you have to find the right balance to figure out what the correct size is to maximize something. And fortunately for us, calculus lets us do a really good job of examining maximums and minimums of functions, right? Um, so let's go back and let's revisit a little bit of things like maximums and minimums of functions and talk about them in a little bit more detail. And then we're going to expand that theory into both being able to present really good sketches of graphs that are more sophisticated than what you could have done in like a college algebra or a pre-calc class, and also to solve this category of optimization style problems. This is something that's a really common use of sort of calculus based ideas in other theoretical sciences. There's also a version of optimization that works through linear algebra that's actually not related but very nice. That's also very so. But nevertheless, having the most efficient way to solve a problem is a very commonly useful thing. Okay, so let's do a couple of quick definitions to recap. Um, so let's let f of x be a function and c be a closed interval. Or a closed domain, the domain. We'll closed interval, it's fine. We say that f of x has an absolute or global maximum at x equals a if for all if for all x in C, f of x is less than or equal to, less than f of a. We say that f of x has an absolute or global minimum at x equals a if for all x in C, f of x is greater than f of a. So we have talked a little bit in the past about relative or local minimum and maximums. This is the absolute or global maximums or minimums. And these definitions are actually pretty straightforward. What an absolute maximum says is that an absolute maximum is bigger than everything else. Okay, it's like everything else, not just everything around it, but everything in the entire function. So for example, this is our function, right? We have an absolute maximum up here. We have an absolute minimum down here. And this peak and this valley here, these are not absolute anythings. They are relative ones, which we talked about previously, but they are not absolute extrema. Any questions about the definition for absolute maximum? So for what it's worth, it's some sources will let there be an equal here, greater than or equal to. This sort of it's a little bit of a weird case. Essentially, it depends on whether or not you think this function has, does this have two absolute maximums? Or no absolute maximums? They're the same height, so they're both bigger than everything else, but they're not bigger than each other. Generally, I'm not 100% sure which side of this I come down on, nor which one I really should come down on. It's something I need to look at. The only reason I'm tentative, so Paul's Online Math Notes uses the less than or equal to definition, which I kind of want to use going forward, but then I lied to you guys about a test problem, and that feels bad. So, because in that case, the function f of x equals 2 has infinitely many maximums and minimums. If we have the less than or equal to or greater than or equal to in the definition. So again, I'm not 100% sure where I come down on it. Either way, most of the things we're doing will probably want to have the greater than or less than or equal to. Just note the absurdity of saying that a constant function is always at its maximum, which I guess is technically a true statement. I don't know. I'm getting into the weeds on this one. So, finding absolute maximums absolute extrema is actually relatively straightforward. An absolute extrema, to find an absolute extrema, first, one, identify possible points where this can occur. So the possible points where an absolute extrema can occur are either at the endpoints of a closed interval, the picture we drew above works, but in general, wherever you start can always be a max or a min. And wherever you end can also always be a max or a min. Because we sort of have that hard cutoff and nothing happens afterwards, as long as we have that hard cutoff, we can identify that point where it ends. We can have a maximum or a min there. As a side note, what if we have an open interval? So we'll look at that same picture there, or a similar one, but instead of having closed dots, we have open ones. Why can't these points be maxes or mins?
Because they're not part of the interval?
Say again?
Because they're not part of the interval?
Right. So what would we be able to identify as our minimum here? Well, let's say this was at x equals 2, right? Well, we could say it's really, really, really small compared to everything else if x is equal to 2.000001, right? But the problem is that x equals 2.00000001 is also on that interval, and it's smaller there, right? So no matter what point you pick, I can always pick one that's a little closer to the open part, right? I can always pick one so that it's smaller. So you can only have this happen at the endpoints of a closed interval. Similarly, if you have if your interval doesn't have endpoints, if you have infinity on one side or the other side, it's possible that you don't have a maximum or a minimum because your function also goes to infinity there. You have to evaluate some limiting behavior. But in general, you should only include endpoints of a closed interval for this. Technically, the set of all real numbers is actually a closed interval, but let's not talk about it. It's not a closed interval, it is a closed set, but whatever. Anyways, the other thing that we can consider, the possible points where this can occur, where we can have absolute extrema, are of course the critical points. And what is a critical point? Guys, remember from 2 weeks ago?
No.
No,
It's
it's
critical
critical,
points
Cam.
are where it where it transitions from positive to negative, or local maximums and minimums.
They can be local maximums or minimums. Adina?
The critical point of a function is where the is that where the derivative is 0?
Or it doesn't
Or-
exist. Yep.
Okay.
So critical points are where f of x is 0, it doesn't exist. And Cam, you're actually really close to being right there, because the thing that can cause this to be a maximum or a minimum is that our derivative might change signs. Our function might change from increasing to decreasing, right? And that horizontal tangent line there gives us a critical point. So critical points are where f prime of x equals 0 or f prime of x does not exist. Once we've given ourselves a list of all of the possible critical points and endpoints, right? Once we have a list of our possible places where we can have an absolute maximum or minimum, all we have to do is just figure out which one's biggest and which one's smallest. That's it. That's it. So essentially what we need to do is we should evaluate at the endpoints and critical points and decide which is largest. There is a catch here. What about f of x equals, say, x squared on, let's do the open interval from -2 to 3. Actually, let's do here, closed at -2. So what are our possible extrema? Well, we have the endpoint on the closed side. It could be at x equals -2. And we could have an extrema at so f prime of x is equal to 2x, which means that 0 is equal to 2x, which means that x is equal to 0 is a critical point. So x equals 0 is another possible extrema. But I suspect that that's not quite going to work out for us, right? So if you look at the graph up here in the corner, I've graphed the function on that interval, and you'll notice that we do get this endpoint here, -2, 4, but we don't get this one up here. We get 3, undefined. F of -2 is 4. F of 0 is 0. So f of 0 is in fact a minimum. But f of negative 2 equals 4 is not actually a maximum. The problem is that we get a lot of stuff that's just bigger than that, right? We can have at 2.83, we get 8.009. Do I have what? Sorry, Nick, I don't understand your question. Oh, yes, I have MX Blues in my keyboard. It's a bad time. Anyways, the limit as x approaches 3 of f of x is 9. 9 is bigger than 4. So this function has no maximum. So what we really need to be checking actually is we need to be looking at not just the closed endpoints, but we need to be looking at the open endpoints and taking a limit at those open endpoints. Okay. So when I say evaluate at the endpoints, so when evaluating at endpoints or any discontinuities, evaluate left and right hand limits. To verify your max / min.
So our our um our absolute extrema cannot be a limit. They have to be a actual value.
Yeah, because if the point doesn't actually exist on the interval, then you can't have extrema there, right? If the point doesn't exist, it can't be a maximum.
No, but you're approaching that point. That's the whole purpose of the limits, right?
Exactly. So we can know if we could be getting, like, for example, another example, f of x equals 1 over x on negative 1 to 1. So we get these endpoints 1 1 and negative 1 1. Sorry, negative 1 negative 1, but they're certainly not extrema, right? It's definitely bigger than 1 on certain parts, specifically between 0 and 1, right? And it's certainly bigger, less than negative 1 on this part of the interval as well.
Right. I get that. I guess what I'm trying to say is like in here, I would say that it seems appealing to say that your absolute extrema, your maximum would be approaching infinity.
It is approaching infinity, but where is your maximum?
It's well, that's what I'm saying. It's approaching infinity versus saying it doesn't have a maximum.
So a maximum has to have a place to be at. So when we're saying that we have a maximum, it must be a maximum at x equals blank of blank.
So in here, where like so on both of these examples, like
Mhm.
it doesn't have a maximum, even though some parts of it are obviously greater than others. We're still
Exactly. Yeah, there isn't one single part that's bigger than everything else. You can't point at a point on the graph and say this is the biggest point. Everything else is smaller.
Okay. Okay.
Right? If you picked on 1 over x, if you picked some point that was arbitrarily close to 0, I could pick one that was even closer to 0. No matter how small your number was, I could cut it in half. Right?
Okay.
Okay. So let's try another example here. Let's consider the function x squared minus 4x. And let's identify extrema on 1 to 3. So first off, let's identify possible extremities. This means we need to categorize endpoints. And discontinuities. And critical points. So first, the interval is closed. So x equals 1 and x equals 3 are candidates. Next, f of x is continuous. So no discontinuities to worry about. And third, let's find our critical points. So f prime of x is 2x minus 4. Means that if 0 is equal to 2x minus 4, that means that 4 is equal to 2x, which means that x is equal to 2. So this is also possible critical point, or possible max or min. And then second, we're going to test the candidates. So we have 1, 2, and 3. And then we just want to know what their different sizes are, so we can just plug them all in, right? 1 squared minus 4 times 1 is negative 3. 2 squared minus 4 times 2 is negative 4. And then 3 squared minus 4 times 3 is negative 3 again. So f of x as an absolute maximum at x equals 1 and x equals 3. And then f of x as an absolute minimum at x equals 2. Generally, absolute extrema are pretty straightforward. They let us just deal with. Um, you're basically just looking for where it's biggest and its smallest. If you actually do have a closed interval in a continuous function, then it is just as simple as saying, all right, I'm going to pick all my endpoints and all my critical points, and we're going to check them and see which one's biggest and which one's smallest. If you have something that's a little bit more complicated, of course, things get a little bit more complicated. Um, this is starting to get to the point where it's harder to give a really nice algorithmic approach to testing every single possible thing. You actually really do have to be thinking, what does this function look like? What happens over the course of this function? Does it have a discontinuity? If it does, what type of discontinuity does it have? Are there asymptotes? Because asymptotes are going to make things really weird, right? Asymptotes, if you have asymptotes in your function, then you're not going to have if you have a vertical asymptote, you're not going to have a maximum or a minimum, right? Okay, so I'm trying to remember what we actually talked about before the exam with regards to this stuff. Did we talk about derivative tests, like first derivative test at all? Have we talked about concavity? I don't think so, because I think
No, I don't think so.
I would have had to have I would have had to have the conversation about convex and concave versus concave up and concave down. Okay. So let's back out of maxes and mins for a second. And let's talk about concavity and the second derivative. So the first derivative tells us whether a function is increasing or decreasing. But that doesn't tell us the entire story, right? If you're increasing, you can increase in a handful of different ways, right? You can increase at a constant rate, right? You could increase at an increasing rate. And you could increase at a decreasing rate. These different types of increase sort of all behave a little bit differently. So what we want to be able to say is we want to talk about what's called the concavity of a function. So we say that f of x is concave up on an interval I if for all I, or for all x in I, the line tangent to f at x is below curve. So in our example here, if we take a tangent line at any point, we'll notice that that's below the curve. So this would be concave up. For concave down, let's see here. Nope, that didn't work. Oh, my. Boy, I wish I could do that on a whiteboard. For concave down, the definition is going to be the same, but we're going to change a couple of keywords. In particular, concave up is going to turn to concave down. And the line's tangent to f at x is above the curve. So pretty much the same definition, just a couple of words change. And so if we look up here and we take a tangent line, you'll notice that this tangent line is below, or sorry, is above. So that means that this one is concave down. In a lot of other parts of mathematics, in particular, once you get beyond anything past calculus, like anything beyond Calc 1 and Calc 2, concave up will be referred to, is sometimes called just called concave, and concave down is sometimes called convex. So if you've heard the term concave and convex in other settings, these are basically related to those. Lenses, for example, often have concavities in them. The way I try to think of it is that for concave up and concave down, the concavity is the side, like you would be concave up if you would be able to you would be able to use it as a spoon, right? If we were to be like this function here, we could put water in it and it would sort of rest inside it. We could see how that would work as a spoon, right? But concave down is somehow an upside down spoon. The water would just immediately fall out, right? Or I guess Jello, because water would technically fall out of that concave up graph as well, wouldn't it? The Jello would stick to it. These definitions for concave up and concave down, while accurate, are unhelpful. They are very difficult to check. Anytime you have a definition that is for all the blank in blank, that means that checking it to prove that it is concave up would mean that you would have to check every single tangent line, and that seems really, really problematic, right? So luckily, there is a way to check concavity at a point by finding the rate, or to find the rate of change of the rate of change. In other words, if we think about our concave up function that we were talking about earlier there, right? It's certainly increasing. And since it's increasing, that means that f prime of x is positive. But at the beginning point, f prime of x was very shallow, right? So we started with a shallow slope. And at the end here, we ended with the much steeper one. So if the slope is kind of pulling upwards, then that means that we're actually concave up. If the slope is tailing off downwards, if we're moving from a very steep slope to a very shallow slope, then we're concave down. So the thing that we take away from this is that we can characterize concavity by saying if f double prime of x is greater than 0, or sorry, if f double prime of a is greater than 0, then f of x is concave up at x equals a. If f double prime of a is less than 0, then f of x is concave down at x equals a. So what is this f double prime thing? Well, it's a case of notation being exactly what you would expect it to be. F double prime of x is f prime of x prime. That is, it's the derivative of the derivative. The derivative tells us the rate of change of the original function, that is increasing, decreasing. The second derivative tells us the rate of change of the derivative. Is it increasing at a decreasing rate? The really common direct application of this is in physics, and it's sort of like the very, very first thing you do in a physics class. So anyone who's taken physics should recognize this. And for those of you who are planning on going into physics, the calc-based physics course after this, this is important. But if you have a position function, y of t, say it's a height function, then y prime of t, the derivative of your position, tells you how fast your position is changing. This is your velocity function v of t. And y double prime of t is v prime of t, which is a of t, an acceleration function.
Hey, I don't mean to interrupt.
Yeah.
Can you just scroll up like 2 lines super quick?
That was 2 lines?
Thank you. Yeah, that's perfect.
Okay. I am possibly going to be able to print this to a PDF file, and then I can post that as well. I'm not sure.
That would be extremely
OneNote likes to print things really gross. I'm looking into some other note-taking apps that actually give me pieces of paper, and then I could make like notes that don't look awful. So we'll figure it out. It'll be good. It's all technology. All right. So anyways, this framework is actually really, really helpful for sort of just considering what's going on. If you think of it in terms of position, you get this position velocity acceleration model. Acceleration tells you how fast your speed is increasing, right? If you're accelerating very quickly, that means that you're going to be going very fast soon. So this lets us actually sort of string together a more sophisticated model for graphing a function. So let's say we have, what do I want to do here? Yeah, actually, let's make a little table. And we're going to have concave up, concave down, increasing, and decreasing. So a function is concave up on an interval. Sorry, it's concave up and increasing means that we get this shape. Concave down and increasing means that we get this shape. Concave up and decreasing means we get this shape. Again, you can kind of picture the water resting inside the spoon. And then concave down and decreasing gives you this shape. So another way of thinking about concavity is in terms of like if you're a business person and trying to decide like, or trying to figure out what the profit or revenue of your company is doing, right? If your revenue looks like this first picture here, right? This, oh wow, that's this guy here, then you're probably pretty psyched, right? Like that's a good thing. Your revenue is going up and it's just going up and up and up and it's going up faster and faster and faster. That means you're doing something right and you should be staying the course, right? If your revenue is going up but it's concave down, right, kind of like this guy here, then you're increasing but you're starting to hit like things are starting to get worse, right? You're approaching a maximum, and so you kind of want to figure out a way to flatten out that curve. If you're like this function here, concave, you're decreasing but you're concave up, then your revenue is going downwards, which is bad. Like you're starting to lose your income stream, but you're managing to level that out, right? So that means that things are looking less bad. Hopefully you're going to go from one of these guys to one of these guys. I'm pointing at my screen like you guys can see that, but hopefully you're going to go from this one to this one. And then finally, if things look like the concave down decreasing type thing in the bottom right hand corner here, life is really bad and you're in a lot of trouble, because not only is your revenue decreasing, but it's decreasing at a horribly, horribly bad rate, and it's getting worse, right? So things are going badly. And by being able to decide what our graph looks like on each one of these intervals, we can sort of give a really, really nice picture of the graph. So, for example, let's consider f of x equals 3x to the fifth minus 5x cubed plus 3. Let's sketch the graph. Using concavity and maximum, or an increasing and decreasing information. So first off, when you're sketching the graph, you should try and look at it, and we're going to try and have some information about where it is going up and going down, right? So to find out, so first, to find out increasing, decreasing behavior, we need f prime of x. So f prime of x is 15x to the fourth minus 15x squared. And 15x to the fourth minus 15x squared is 15x squared times x squared minus 1. So that's probably good enough for what we want. To find out concavity behavior, we need f double prime of x, which is the derivative of the derivative, so that would be 60x cubed minus 30x squared, or 30x, which simplifies to 30x times 2x squared minus 1. So we can use our first derivative to figure out our critical points. These are potential maximums or minimums. This is where our function can turn around, right? So what are our critical points? Well, we have one at x equals 0 from taking the 15x squared and setting it equal to 0. And we have another one at, or we have two more at x equals 1 and x equals negative 1. That's from setting x squared minus 1 equals to 0. So those are our critical points. We want to know the possible places where our concavity changes. These are called possible points of inflection. And here we have one at x equals 0 from the 30x. And then we also have some at x equals 1 over the square root of 2 and x equals negative 1 square root of 2 from setting 2x squared minus 1 equals 0. And then I'm going to make a really big sign chart. I'm going to include on this sign chart all of my critical points and all of my possible points of inflection. So we have 0, we have 1, -1, and then we also have 1 over the square root of 2 and -1 over the square root of 2. And on each of these intervals, I want to know the sign of f prime of x and the sign of f double prime of x. Much like we did with intervals of increase and decrease, and much like you should have done at some point in college algebra, if we pick a single point on each of these intervals, that's all we need to test. It'll tell us the entire behavior for the whole interval. So we can just plug in some point on each interval to find our behavior, right? And it turns out that what we should end up with is f prime of x will be positive, negative, 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 positive. I'm just drawing these dotted lines to show the splits on the intervals. And then f double prime of x, the second derivative should be negative, negative, positive, negative, positive, positive. And if you want, you can verify these by plugging in some points. There's a lot of points to plug in, so I'm going to save you the time of plugging it into a calculator, or just plugging it in by hand. You can also save yourself some time by only testing points where things are relevant. For example, you know the first derivative cannot change signs at -1 over the square root of 2. That's not a critical point, so it won't change signs there, right? So the only place it can change signs is at -1, 0, and 1. So that's, you know that once it's negative here, it'll also be negative here. And now we can kind of get an idea for what this looks like by using our box from before, this box. We can essentially fill in each one of our intervals with a shape that looks like this. Okay, so we're going to start as increasing but concave down. So our first interval, we're going to be going uphill, but we're going to be slowing down. And then we change, our first derivative changes signs from positive to negative. So we need to turn around at -1. So we'll have a maximum there. And then we'll go to, at 1 over the square root of 2, will be concave down and decreasing. So we get one of these. And then at some point around -1 over the square root of 2, our concavity is going to change. So we're still going to be going downhill, but we're going to be leveling out. So maybe something like this. We do have a horizontal tangent line at 0, so we'll be flat there. But at 0, we don't actually change signs, so we're going to be decreasing again. And we're going to be decreasing with concavity downwards. Our concavity is going to change from upwards to downwards. So we'll get one of these shapes. And then at 1 over the square root of 2, our concavity will change again to concave up. We're still decreasing though. And then finally, on this last interval, we'll change to increasing concave up. And we'll get something that looks like that. So you can see where our intervals ended up on our graph here. Oops, that's a bad dotted line. Should be there. And then if we wanted to, we could do these, one of these. And that should be pretty good. And in fact, let's go actually graph this function. Let's use Desmos real quick. Let's graph 3x to the 5th minus 5x cubed plus 3. And then let's make this, let's do our window between -2 and 2. That looks like a pretty okay sketch to me. So this lets us sort of figure out exactly where all of those weird shapes that happened, right? If you were trying to graph this in a college algebra class, you'd be kind of stuck because there's a lot going on that you can't really interpret here. Why is this maximum over here? Why is this maximum here? Why is this minimum exactly here? What is this wiggle doing? Okay. So graph sketching is it's relatively involved. There's a lot to it, but once you've practiced it a couple times, it shouldn't be too much. So I think I'm gonna call it there for lecture stuff. Does anybody have any questions about the process I just walked through here? That.
Are you gonna put a recording up of this lecture?
I am, yes.
Cool, thanks.
And I will try to print out this the note sheet as well and post it to Discord.
So are we done with class right now? Or
So basically right now, and I'm trying to figure out a way to do interaction a little bit better in the future, but my plan for this instant is to say, okay, we are done with lecture, which means that you guys, if you do have something you absolutely need to do, then you can walk away from your computer or whatever. I am going to post some practice problems in the form of a worksheet, and I will essentially be on call, and so will Katie. We'll be on call for the next hour and 20 minutes or so until the scheduled end of class. So if you have any questions about the problems that you're working on, you could pop into one of the voice channels and ask us, or you can just type something into Discord and we'll be here watching. So I will post a quick worksheet or two, and you guys can get started on those. The voice channels, voice 1, 2, 3, and 4, I will be setting those up so you can use voice activation in those channels. So you don't need to be using a push to talk in there if you're not super comfortable with using voice activation. And you guys, I'm going to give those spaces you guys can use to sort of talk about the problems, and you guys can like share your screens if you're working on a tablet or something like that, where you can show people your work and stuff. So think of them as like study rooms.
And I know, have the test scores been posted for everyone?
I believe they have, yes.
Are we going to be covering that this session, or will we be covering that Thursday?
The test?
Yeah, were there any things that you saw, any trends that you wanted to cover and go over?
No, I went over the test last week, or the week before last. There's a video on the YouTube channel of it.
Thank you. My mistake. I wasn't able to attend last week.
That's okay. Attendance was very much not mandatory because class was canceled. So. All right, let me grab this practice sheet. And then... Actually, I'm just going to give you guys some problems from Paul's online math notes. Because that seems like a reasonable course of action. Let's do this, and then we'll do 1 and 2, and then 5 and 6.